In this short video, we consider a square lamina that lies above the xy plane and parallel to the xy plane and lying above the xy plane at a height 1 unit. This square is expressed by means of Cartesian inequalities like this: 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, and z is equal to 1. That means this square lamina consists of triples x, y, z, where x varies between 0 and 1, y varies between 0 and 1, but z is always 1. That means always the third coordinate, z coordinate, is always 1. That means such triples lie on the plane z is equal to 1. So this square lamina is a portion of the plane z is equal to 1. Now we plot this square lamina like this by noting point on the z-axis, which is the point 0, 0, 1, because in this inequality also we can consider x equal to 0, y equal to 0, and z is equal to 1. We get this point. What happens when x becomes the maximum value 1, but at the same time y equal to 0? We get this point 1, 0, 1. Then what happens? X is equal to 1, y is equal to 1, and z is equal to 1. We have this point triple 1, 1, 1. At the same time, when y is equal to 1 and z is equal to 1, x is equal to 0. We get this point 0, 1, 1. Now we consider the boundary of this square lamina. This boundary is the union of 4 line segments. One line segment is from A to E, that is from 0, 0, 1 to 1, 0, 1. Another line segment from 1, 0, 1 to 1, 1, 1. Another from triple 1, 1, 1 to 0, 1, 1. Then another from 0, 1, 1 to 0, 0, 1. And we are going to parameterize this line segment, and we consider the parametrization, and also we consider the vector valued function that represents the line segment. We note that on this line segment z value is always 1, okay. Y value, y coordinate is always 0, but at the same time x values vary from 0 to 1. So the vector valued function that represents this line segment is si plus 0j plus k, where s varies between 0 and 1. See, on this line segment only the x coordinate varies from 0 to 1. At the same time y coordinate is 0 and z coordinate is 1. So we have this vector valued function r of s is equal to si plus 0j plus k, where 0 less than or equal to s less than or equal to 1. Now on this line segment we can see that z coordinate is always 1, so we can write k here. X coordinate is always 1, so we have I here. At the same time y coordinate varies from 0 to 1, so we have the vector valued function given by r of s is equal to I plus sj plus k, where 0 less than or equal to s less than or equal to 1. On this line segment from 1, 1, 1 to 0, 1, 1, z coordinate is 1, y coordinate is 1. At the same time x coordinate varies from 1 to 0, 1 to 0. So we take 1 minus s here, so, and s varies from 0 to 1, so that when s is equal to 0 this becomes 1, so I plus j plus k, that corresponds to this point. When s is equal to 1 we reach this point, because when s is equal to 1 we have 0 I plus j plus k, which corresponds to the point 0 1 1. Then on this line segment from 0 1 1 to 0 0 1, z coordinate is 1, no problem. X coordinate is 0, so 0 I here. At the same time, y value varies from 1 to 0, so we take 1 minus s here, where 0 less than or equal to s less than or equal to 1. So this is the parametrization of the 4 line segments, that is the boundary of this square. See, one thing is very very important, the orientation from A to E, then E to F, then F to D, and finally from D to A is very very important. And also we see that on this line segment, the derivative of the vector valued function R of s with respect to the parameter s, that is dr by ds, is 1I plus 0j plus 0k. So we ultimately get I. Okay, that is dr by ds is the unit vector I when 0 less than or equal to s less than or equal to 1. Now what about this one? Here on this line segment, dr by ds is equal to 0I plus 1j plus 0k. So dr by ds on this line segment is j. dr by ds on this line segment is negative I. dr by ds on this line segment is negative j. The orientation along the line segments is shown in the figure.